Hello, everybody. Nice to be back again with IPIC in an online meeting. So again, I talk today about what we can do for optical computing. Basically, we can print micro optics to have lower loss of coupling. This is a little bit based on a project we have right now. It's called the Phoenix project with a couple of partners. IBM, one of the speaker here, is also involved in this project. The motivation is basically that the AI demands a lot of computing power. You have digital electronics who struggle to satisfy with this. So photonics is a possible additional solution. It's not the only solution. Electronics will always be there, but it's a possible solution. Just very quickly to who are we, Nanoscribe, those who still don't know us yet. So we are not a startup anymore. We are industrial the company right now. We are 100 people, close to Karlsruhe. We have offices in Shanghai and Boston, several patents to support our technology. And this is just look into our one of our process development labs, where we have some colleagues doing some studies for feasibility for different applications. What is maybe not known in this area group here of people is that we, since September, so now 6 months, we are part of the Lab 14 group. Lab 14 is not known very well outside of Germany, as far as I'm informed. So basically, one of the most known is probably Heidelberg Instruments. So we are now together with Heidelberg Instruments. I think that's going to be very interesting for the future. But coming back to the subjects, so what we can do, we can print optics and enable enhance photonic packaging, bright connections, lower losses. So we can use our technology with this kind of 3D microprinting. It's based on 2-photon lithography for photon integration in a large variety of application. The main application right now is here quantum computing and optical computing. So this was well presented already by previous speakers previously. And how can we do this? Basically, we have a femtosecond lasers, we have scanning mirrors, and we concentrate the light into a resin. And we can also additionally, not only concentrating the light, we can also, with our patented grayscale technology, we can tune the voxel very, very quickly at 100 megahertz while scanning. So instead of having, for printing optics to enhance the coupling, having tens of slices to have a very smooth surface, we can do a single slice and have this intra-sliced tuning of the voxel, which helps to have optical quality and then very low losses for coupling. So coupling, what do you want to couple? What do you need to couple? In integrated photonics, you couple from a waveguide to a fiber. So you have seen the difference here. So you have this waveguide in the simulated electric field here. So that's 200 nanometer. And if it's at scale, look at a single mode fiber, 1550, 5 microns, you see what is the difference. So if you would just use this and couple to each other, you will already have minus 7 dB loss. You don't want that. So we can basically print an optic to match these different mode fields. So focusing or collimating depends on what you need. Additionally, especially the 1 dB ratio, when you position two optical waveguides or optical elements next to each other to couple light, you can say roughly that's a quarter of the mode field diameter is a lateral tolerance. So for a 5 micron or 10 micron diameter single mode fiber, this would be 2.5 micron. You still will need some very precise positioning systems. We can do optical, we can do collimated lens coupling with 25 microns, and you add some 7 microns and more. So we can expand the beam. In the project I've mentioned, we have shown this at different locations. So one location is basically fiber to chip coupling. You can see this in the scheme here. So that's between the ENP and the photonics PIC device. So for this, we use our in-house software where we can add, do the design of a fiber array, basically. We can have the design of the collimated lenses. You just enter the lens formula. This is the orange part. Then you can say this, I want to have in optical qualities. This I want to print fast, or I want to have good adhesion. So there are a lot of standard recipes already included in our software. And then you can do the collimating lens on the fiber. You can do this in batch processing. On the other side, on the chip sides, again, we can do the lens formula STL, and we also can very precisely print the lenses by the scanning mechanism, but also we can detect. So we use you can see here on the upper area, let me quickly put on this laser pointer. So we use double square or circles or crosses, whatever you might, fiducials on the chip to detect where is the waveguide. We can also detect the waveguide, but that is not as precise as if you have fiducials, or it basically will take more time. Most of the time, fiducials are sharper in detections, and then precisely position to these fiducials the optical lens. So we adapt the optical, the shape of the optics, the printing of the optics to the edge and to the position in 3D of the waveguide. Also, basically what we have in-house is a simulation for this kind of optics, as you see here on the upper area in X and Y. We have a tool for measuring these beam profiles for certain wavelengths. 1550 is clearly possible, green light too. And then if you look at the overlay, you can see there's nearly no mismatch. It's perfectly. So this is basically the best way to couple between different optical platforms. Here's an example. So we coupled from a fiber to a PIC chip. And in this case, we had 1.3 dB, not the 1 dB, Anna, I'm sorry yet, but we can go there. So we can maybe discuss about that offline or in another call. You can see here also some print times. They're not yet fully optimized, but so 2 minutes per lens on the SOI chip and around, as mentioned already, 45 seconds per lens on the fiber side. This is a larger view. Last but not least, we can not only print beam shaping optics, but also imaging optics. So this is from a design from Print Optics, a customer and partner from us. And this is for endoscopes. So, and we have other colleagues who have done optics for optical arbitrary momentum. Please don't ask me how this has been done, but a previous speaker mentioned this. We can discuss about this, or can put in contact with my colleague who has been doing the design. So the technology opens wide possibilities for printing different elements, optical elements, and other things. Last but not least, we can do this scalable and at high performance. You see here the technical specs which are possible for the optics in shape accuracy and surface roughness. We can do batch processing for fibers. We can do batch processing in trace on gel pack of single dyes. We can do it at wafer level if it's required and makes sense that you always need to look at. Yeah, so we offer this for photonics industry. We have a couple of awards we achieved. This is for having high quality, faster production. And as I mentioned before, we do the software, do the hardware, we do the printing materials. We bring it every year, it's a new printing material. And we are located here in this nice building. So if you are interested and you have a challenging project, contact me and we can see if we can help you with our system to solve it.